Today we're gonna talk about the stresses developed on a thin wall pressure vessel. So let's consider first is the cylindrical vessel. Okay, so let's assume that we have a cylindrical vessel that has the wall thickness is T, and the inner radius of that cylindrical vessel is R. Now we would like to see what is the stress in this longitudinal direction and what is the stress in circumferential direction, which is you can imagine along this circumference, right? What are the stresses? So along the circumference direction, we can see that the stress is sigma 1, and along the longitudinal direction is sigma 2. So let's take a look on the sigma 1 first, how we can determine that one. So if I take a cut right here and here, basically in this element, then I in the right side here I already drew this diagram. So let's consider the length of that strip is dy, okay, and thickness is already given, which is t, right? And then the radius of this element is or this cylinder inner radius is r. Now we can see that the stresses, basically the sigma 1 is developed on this face and this face. So this is sigma 1 and sigma 1. Now also, if we can imagine that this section or this particular plane, right? So let's say this particular plane, excuse me, actually if I can draw it in this way, right? So this particular plane also experiencing a pressure, right? Because the cylinder has a fluid and that fluid has the pressure P, right? It is experiencing that pressure, which is P. Now we can have two different forces. One is due to that stress and one is due to that pressure. So we know that the axial stress definition, sigma 1 equals to force divided by area. So basically force would be sigma 1 times A. And we also know that pressure definition, pressure is nothing but force divided by the perpendicular area, and then F equals to, so let me write it PR, which is force due to that pressure, times P times A, right? So that means two different forces acting but in two different direction. So in this direction, again this is the y direction and circumferential direction is x and the vertical direction is z. So we are looking into x direction actually. So now if we take the summation of force or equilibrium equation, Fx equals to 0, let me make sure that transfer this coordinate system. So this would be y longitudinal direction, this is my circumferential direction, which is x, and maybe this direction is, or vertical direction is z. So I'm taking the force balance or doing the force balance in x direction. So now it would be the force due to that stress, basically sigma 1 times the area, right? So the area of this small section is nothing but the dy times t, right? Which is, or t times dy. Now I do have this section 2. This is one section and this is one section, okay? So I have to multiply this by 2 minus P is acting in opposite direction compared to this sigma 1, which is the pressure times the area. If we can, if we consider this is the total 2 times r, which is the 2 times the radius, and then this length is dy. So it would be, let me write it here. So it would be 2r times dy, which is equals to 0. Now if we do solve this equation, so it would be 2 sigma 1 t dy equals to p 2r dy. So dy is gone, and then 2 is gone. So we'll have sigma 1 equals to pr divided by, excuse me, PR divided by T. So now this is the expression, actually the circumferential stress, right? We also call it hoop stress. So we got the expression for this sigma 1, which is acting in circumferential direction or circumference. Now let's take a look on the longitudinal direction, which is, we call this direction is longitudinal direction, right? So if we would like to get the sigma 2, then we are taking the cross section. Let me just remove all those. Okay, so we are basically taking the cross section right in the middle of this cylinder. Okay, now if we take the cross section, then we can see that sigma 2 is basically acting on this strip, right? Sigma 2, or in this thickness. And also we can see that this, or we should realize that this, if we consider this inner area, or this section that has the radius of r, right, radius of r, then this is also experiencing a pressure force, right, perpendicular to this surface pressure force, right, which is P. Now if we do the force balance summation of Fy, again this is y, this is z, and this is x. So we are doing along the y direction, then it would be sigma 2 times the area of this entire strip marked by the red lines. It will be basically twice pi r times the thickness, which is T, right, and then negative pressure times the area, cross-sectional area of this inner part, which is pi r square, okay, equals to 0. So if we solve this, sigma 2 times twice pi r T equals to P pi r square. Okay, so pi is gone, r and r square gone, then it would be sigma 2 equals to P r divided by 2T. Okay, so this is the expression for longitudinal stress, right? So now we know that sigma 1 and sigma 2. So this is sigma 1 and this is sigma 2. So let's take a look what is the relation between these two. Okay, so we know that sigma 1 equals to PR divided by T, and sigma 2 is basically PR divided by 2T, right? That means the relationship between the sigma 2 or sigma 1 equals to 2 times sigma 2, right? Which means that hoop stress, this is hoop stress, and this is longitudinal hoop stress is double then or 2 times of longitudinal stress. So if your longitudinal stress is, let's say, 5 megapascal, then your hoop stress would be 10 megapascal, right? So that means circumferential stress is always greater than the longitudinal stress. So what is the meaning of this? So meaning of this is that whenever we see any pipe or any pressure vessel, or that has the internal pressure and also the thin wall, we mostly see the failure in this direction. Why? It's because we just saw that the stress in this circumferential direction, which are sigma 1, right, these are the sigma 1. So this sigma 1 are basically is contributing to create the fracture along this line. So whenever we do see the failure, we'll, no matter what type of pipe or pressure vessel, will always especially if it is a cylindrical pressure vessel, for sure we will see always the pressure the failure is happening just like in this direction, because of this sigma 1 is basically is contributing or trying to tear apart. So that's why we do see this type of failure. So now we know that the sigma 1 for cylindrical pressure vessel, sigma 1 is always greater than sigma 2. Now let's take a look on the other pressure vessel, which is the spherical pressure vessel. So if we do have a spherical pressure vessel, then basically for this spherical pressure vessel, if we consider this is y direction, this is z direction, and this is the x direction, no matter which direction we are taking, or no matter which direction we are taking the cross section, it would be basically the the stress would be the same, right? So if we take a cut right here, then the stress will be equal to the if we take the cut right here. How? Let's take a look. So if we, let's say we are taking the cross section right here, just like this way, right? And then if we take the cross section, then we can see that in this red strip the stress is acting outward direction, which is actually the sigma 2, right? And because we in the previous problem or in the previous case, we see that if we take this cross section, then we are taking the sigma 2 longitudinal direction, right? So if we do the sigma 2, and then in this cross section, which is circular cross section here, it is also experiencing the pressure force, right? So I can write it. So it is experiencing the pressure force, which is pressure P. So due to that pressure, there will be a force as well. So for this particular case, again, if we do the force balance, right, summation of, let's say, still if we are considering this is y, this is z, and this is x, then summation of Fy would be 0. So it would be sigma 2 times twice pi r times the thickness, okay, because the thickness of this ball is t, right? Minus the pressure is in opposite direction, which is pressure times the area is pi r square equals to 0. Again, if we do solve this one, we'll get sigma 2 equals to pr divided by 2t. So that means for spherical pressure vessel, sigma 1, there is no sigma 1, it would be only sigma 2, which is the the longitudinal stress. And also in this type of structure, if we keep increasing the pressure, internal pressure of this structure, then we cannot really say which direction it will gonna fail, because there is no sigma 1, so it can fail in any direction, right? So now we know that the expression for the cylindrical pressure vessel and also the spherical pressure vessel. One last thing, which is the most important thing, when we will do the this theory or the sigma 1 and sigma 2 expression is applicable only if this condition is matched, which is r divided by t is greater than 10, right? So if this condition match, then it is, this problem is a thin wall pressure vessel. So when we'll solve the problem, we need to make sure that we do this thing first, which is radius divided by thickness, and which we need to see whether that one is greater than 10 or not. If it is greater than 10, then we can use the formula for sigma 1 as well as the sigma 2. Okay, so with that, I'm going to concluding this lecture, and we'll come back with the math problem. Thanks for watching this video.